air over a wing, blood through a heart valve, smoke curling off a candle. The equations that govern all of it have been known for nearly 2 centuries, and for almost any real shape, nobody can solve them with pen and paper. Computational fluid dynamics is how we get answers anyway, not by solving the equations exactly, but by letting a computer approximate the flow, one tiny piece at a time. Before any of the details, here's the whole idea, start to finish. The governing equations, the Navier-Stokes equations, are a set of coupled nonlinear partial differential equations. For a handful of idealized cases, flow in a straight pipe say, you can solve them by hand. For a real wing, a real artery, a real engine, you cannot. There is no formula. The geometry is too complicated and the equations are too tangled together. So instead of chasing one clean solution, CFD takes a completely different route, approximate. Step 1. Stop trying to describe the fluid everywhere at once. Take the region the fluid was in, the air around the wing, the blood inside the vessel, and chop it into a huge number of tiny cells. Thousands, millions, sometimes billions of them. This grid of cells is the mesh, and it's the stage on which everything else happens. Instead of a smooth, continuous field, you now track the flow as one set of values on each little cell. Step 2. On every cell, enforce the same physics. Conserve mass, conserve momentum, but only approximately, written in terms of that cell and its immediate neighbors. The derivatives in the equations, the rates of change, become simple differences between adjacent cells. A smooth statement about continuous change turns into plain arithmetic linking each cell to the ones around it. Do that for every cell, and the single impossible differential equation becomes an enormous system of ordinary algebraic equations, millions of equations, millions of unknowns, but just algebra. Step 3. Solve that system. It's far too big to invert directly, so the computer guesses, checks how badly each equation is still violated, that mismatch is called the residual, nudges the values, and repeats. Pass after pass, the residuals shrink. When they're small enough that the cell values stop changing, you call it converged. That converged field is your approximate solution to the flow. Zoom out, and a CFD study is always the same pipeline. Start with the geometry, the shape the fluid moves through. Mesh it into cells. Set up the equations and the boundary conditions, what's happening at the inlets, the outlets, and the walls. Hand it to the solver and let it iterate to convergence. Then post-process, turn those millions of numbers into pictures and quantities you actually care about, where the pressure peaks, where the flow separates, how much drag the wing feels. And here's the honest part. Every step in that pipeline is an approximation, and every approximation is a place error can creep in. Too coarse a mesh, and you miss the physics. The wrong numerical scheme, and your answer smears or oscillates. Turbulence, which is most real flows, can't be fully resolved, so it has to be modeled. A CFD result is not truth handed down, it's a careful estimate, and trusting it is a skill you have to earn. That really is what the rest of this series is about, each piece of this pipeline, and how to get it right. So that's CFD in one breath. The fluid equations can't be solved by hand for real shapes, so we chop the domain into millions of tiny cells, turn the calculus into arithmetic on those cells, and iterate a giant system until it converges. Geometry, mesh, solve, post-process, with a healthy respect for the approximation at every step. Everything else we'll cover is a detail living inside this one picture. That's all for this video.